Hello and thanks for tuning in to watch the pre-lab video for the determination of an equilibrium constant experiment. This experiment is part of the General Chemistry 2 sequence at York College of Pennsylvania. The goal of the experiment is pretty clear. We're going to try to find the equilibrium constant of a reaction. The reaction that we'll be working with today involves the dissociation of an acid-base indicator. I'll get to the specific reaction in a couple of minutes. But first, let's do a little bit of background on equilibrium and work through the pre-lab problems to make sure we understand the concepts that will help us in our laboratory experiment today. So the first pre-lab question asks us to write the equilibrium constant expression for the reaction involving the dissociation or decomposition of dinitrogen pentoxide. So 2 N2O5s produce 4 NO2s and an oxygen. The equilibrium constant for any reaction would involve the product concentrations, so our products are NO2 and O2, multiplied by one another, each being raised to its respective coefficient, called its order. So we represent concentrations with brackets around a chemical symbol. So we would need NO2 raised to the 4th power times the concentration of O2. No power, or it's 1 because its coefficient is 1. And then we divide by the concentrations of our reactants raised to their orders, their respective coefficients. So it would be NO2 to the 4th times O2 divided by N2O5 squared. Now we would exclude from this expression any species, any chemical, that is either a solid or a pure liquid. For this reaction, although I haven't written them, you'll see in your lab manual, these are all gases, and therefore they could all be and should all be included in the expression here. Question 2 follows up directly on this first question, saying, all right, well, calculate the value of the equilibrium constant if you have measured these 3 concentrations at equilibrium. So our KEQ would simply be, we'd plug in our numbers. Our NO2 number, 0.0128 raised to the 4th power, times oxygen, 0.106, divided by 0.0540 squared. When you take into account those exponents, you should come up with a pretty small equilibrium constant of about 9.76 times 10 to the negative 7th. Now technically there would be a set of units on this equilibrium constant. In this case it would be molarity raised to the 3rd power. But because the units vary with the coefficients, which lead to the orders of our concentrations, we tend to leave off the units of most equilibrium constants. So it's fine if you don't put units on your answer for this particular problem here. All right. Now what's interesting about this reaction, and any reaction that's equilibrium, right, is that this number should always be reached, regardless of where we started this reaction. In question 2, we have no idea where these respective concentrations began, but they have settled in this ratio to give us the 9.76 times 10 to the negative 7. If we try this reaction a different day, but at the same temperature, that would be the one thing that would have to be constant, and began with different amounts of N2O5, NO2, and O2, okay, than we imaginarily began with in this case, we would still arrive at this number. Although these 3 numbers might be different, the 3 numbers we would get would combine in this formula to still give us 9.76 times 10 to the minus 7. And that will be one of the ideas that we're putting to the test in our lab today. You'll measure your equilibrium constant 3 times, each beginning with a different set of initial conditions, very slightly different. And hopefully you'll still get the same combined ratio, proving the name equilibrium constant in that experiment. Okay. Now, pre-lab question 3 relates a little bit as well to how you're going to achieve the goal of today's lab. So let's consider this. We've got the decomposition of hydrogen iodide. Everything is in the gas phase, again, in this reaction. And we're told how much hydrogen iodide we began with. We began with 0.2 moles, but in 2 liters. So we actually have a 0.1 molar concentration of our hydrogen iodide. And we have none of either product species at the start. A typical way to start a reaction, right? With only the reactants present. Now what I've set up on the left side of this here, table here, is what we call the ICE table, the initial change in equilibrium, okay? Or an equilibrium reaction table. We're going to lay out the changes that occur to help us find the equilibrium concentrations of each one of these species. Okay? So we're told that one other number is measured in this experiment, that at equilibrium the concentration of our hydrogen iodide is now only 0.078 molar. Okay? So the initial concentration of hydrogen iodide plus the change equals the equilibrium concentration. So we can pretty easily see that, all right, we had 0.1 molar minus some change equals 0.078. So our change, delta here, okay, is going to be negative 0.022. Right? But symbolically, the change in hydrogen iodide is double the changes in these two. This change row, remember, matches the ratio of coefficients of our chemical reaction. So we could say this is minus 2x. We know it's minus because it's decreasing, and that each of these would be increasing by x, an equal amount. Right? In other words, each time I break apart 2 hydrogen iodides, I form 1 hydrogen and 1 iodine over there on the product side. Okay? So this 0.22 or 0.022 equals the negative 2x that we have up here. That would mean that x is 0.011. Just divided both sides by 2. Okay? So that allows us to fill in what each of these would be. They are, because x is equal to 0.011, then at equilibrium, each of these would be 0.011, because we began with 0 and added 0.011. So we've figured out what each chemical's concentration is at equilibrium simply by measuring one of those concentrations at equilibrium and knowing how it changed relative to its starting value. We'll use this idea to help us get one of our concentrations today. Right. Now we'd like to get the equilibrium constant of this reaction. So the equilibrium constant, the KEQ, would be, in terms of our products, our hydrogen, H2 concentration, times our iodine concentration, divided by our hydrogen iodide, which needs to be squared because its coefficient is 2. Right? That coefficient has a really important role here. Not only did it double the change to our hydrogen iodide relative to the other chemicals, but now it also is squaring that concentration. So if you omit those coefficients, your answer is really going to be off. So now we would take our 0.011 times 0.011 divided by our 0.078, which needs to be squared, and we would get 0.020 when it's rounded for 2 significant figures for the answer there. So that's the equilibrium constant of the hydrogen iodide. Again, if we began with a different quantity up here, all right, at the start, we would still arrive at 0.020. What would change would be the amount of reaction that occurs. In that case, if we had more HI, we would expect a little more hydrogen and iodine to form, so that their numbers are increasing a little bit to keep this ratio constant. That's what's really neat about an equilibrium constant. So what's today's reaction? we're going to be looking at an indicator, an acid-base indicator. And the formula is quite complex, so I won't use the entire chemical symbol on the, to show it on the board. But we can treat our indicator as HIN, and it has a -1 charge on it already. Okay, it's been put into solution. It's dissociated from its cations in its salt form, and it now has a proton though. So when it's put into water, it donates to water, generating some H3O+, and the remaining IN, the indicator, with a 2- charge on it now. So the equilibrium constant for this reaction, Kc, because we're using concentration, is going to be found by taking the concentration of H3O+ times the concentration of In2- divided by the concentration of HIN1-. So what we need to come up with our Kc is these three values at equilibrium. Well, the H3O value should be pretty easy. We can quickly get H3O for any solution because we know that H3O is related to the pH. So we can simply measure the pH of our solutions, of our equilibrium solutions. Measure the pH at equilibrium. And then if we solve this, we would see that the H3O concentration would be 10 to the negative pH. And this would be substituted in there. So that's pretty easy and pretty direct. It's the other two that we have to do a little bit more work to come up with their concentrations. We're going to use UV-Vis spectroscopy like we have in a couple of other cases this semester to measure one of these two. Both of these are active in the ultraviolet and visible region, and they have different absorbance spectrums. So if we looked at the absorbance across all the wavelengths, one of them would look something like this, all right? And the other would look something like that. Okay? So they absorb at two very different wavelengths. At first glance, it might seem like, well, we could pick either wavelength then, and if we recorded data like we have in the past for absorbance versus concentration, we know that a linear relationship would exist. A equals BC. We could measure our unknowns and solve for the concentration from the absorbance. Beer's law, which we've used before. But which wavelength should we choose is the question. And we want to choose this wavelength here because there's little or no absorbance of the other species. Both of these species will be mixed in our container that we're trying to measure the absorbance of. So the total absorbance that we get is actually the sum of the two species contributing. So we want a wavelength where only one species is contributing so that the absorbance comes from only that species. Okay? And maybe it's actually going to be a little bit closer to this, where the first species is completely gone down to zero. At this wavelength, I've got a significant absorbance coming from the species that I've drawn in green and also the species that I've drawn in black. And we won't know when we just measure one value how much is coming from each one of those species. So that's a poor choice, and we'd rather choose this one. So the first thing that you'll do is you'll form a solution in lab today where you force this equilibrium far to the left side. How are you going to do that? Add acid. When you add H3O, you drive the equilibrium back to the left side. That's Le Chatelier's principle in play. And so then you could have a totally protonated version of your indicator. Measure its absorbance spectrum. I believe that will be this one. Okay? Then you could totally deprotonate. Take all of the H's off. Now we don't see it in here, but if we replace the water with OH-, strong base would take all of these hydrogens off of the indicator and move us over to the product side. Okay? I believe you'll get this spectrum then. Pay close attention because you'll see, your eyes will see two different colors. The reason you're seeing two different colors is because of what's getting absorbed. That's what this tells us. What colors are being absorbed by the two different solutions that we see. So when one solution absorbs very short wavelengths, 400s and 500s, and it's taking out or absorbing the blue colors that are in white light, visible light. And so what's left and not absorbed is the color that is reflected and that your eye sees. So that solution should appear reddish yellow, most likely. On the other hand, the one that I've drawn in green is going to be absorbing the top end of the visible spectrum, 700s, the reds and the oranges. So what's left to be reflected is the blues, and it should be a very deep blue color that you see. Okay, because what you see, again, you see the opposite or the reflected colors. The not absorbed colors of the solution. Okay? Everything obeys this law. The reason blue jeans look blue, they are reflecting back the blue colors and they're absorbing the other colors. And our solutions are just like that. Okay? So, to get back to our lab, once we've established which wavelength we want to work at, we can measure, and it should be for the IN-2, we should be able to make essentially a very quick and easy Beer's law relationship for the IN-2. We'll actually just do it for 1 point. Okay? For a single point, you can have essentially a graph through 1 point, and 0, 0 would be your other point. And that's how you'll get your B. And then you would solve for the amount of the deprotonated indicator at equilibrium from your A equals BC. So your concentration will be A divided by the B value that you'll find. Okay? You'll get B from the stock solution that you prepare and test, and then you will use that to calculate the concentrations of your equilibrium systems. So all that leaves now is HIN. Okay? Now, in reality, we're setting up an equilibrium table to find HIN, but if we just think about what's going on underneath our HIN with our initial change in equilibrium, we'll know how much we added to this initially. This will be something you physically measure, and then you will know the change, because the change, the indicator of deprotonated will start out at 0, and you're going to get the X from up here. See, the value of the amount of the deprotonated indicator that shows up at equilibrium is the amount that gets lost or decreases from the HIN. This is just like the hydrogen iodine question that we had a few minutes ago, right? The amount of H and I that formed in that reaction was equal to, in that case, half of the HI that disappeared. But here it's a 1-to-1 relationship, so the amount of IN2- that appears equals the amount of HIN that disappears. So at equilibrium then, it'll simply be the initial amount minus that X, or minus the concentration of the IN-2. And this would be the amount that you would plug in to your equilibrium constant expression. Now the way that you'll vary this reaction is that you'll have 3 different pHs that you work at, where you are not beginning with a 0 for H3O underneath it in the reaction. You're actually going to be supplying a bunch of that, and that's going to alter the amount of reaction that actually occurs. So your X would be very different for your 3 different cases. And what we'd hope is that although X would be different, that would change this, and all 3 numbers would shift to hopefully maintain a constant for our equilibrium constant. Okay? So that's one of the things you'll be asked in your lab report sheet, is to consider, how consistent, how constant are the values that you arrived at in the experiment. And so I just want you to think about that. Careful measurements can lead to good results here. When it calls for 1 milliliter, use a pipette to get exactly 1 milliliter. Don't use a graduated cylinder where it would be more of an approximate 1 milliliter. Try to be as accurate as possible if you want to get a nice, consistent set of equilibrium constants. Right? We're going to use a pH meter to measure these values. And so that pH meter needs to be calibrated to make sure that it's accurately recording your pH values and thus your H3O concentrations. If that calibration is off, that introduces a systematic error in your results, right? Because if this is constantly too high or too low, there's no way that your numbers are going to be consistent in your equilibrium constant calibration. Our UV-Vis spectrometer needs to be zeroed out at the appropriate wavelength once you've decided which one you're using. Again, if it wasn't, then you would have a systematic error in your absorbance values, which would lead to a systematic error in the concentrations of IN-2. So you can see how these things propagate if you're not careful in following your procedures. They lead to these systematic errors. Okay. With any luck, you'll arrive at a nice consistent set of 3 values for your equilibrium constant, and you'll have a good time studying the equilibrium constant of an acid-base indicator. Good luck.